So during the first part of this lesson about the lithium-ion battery, we have described the main advantage of these batteries and the main features, so the compositions of the negative electrode, the compositions of the positive electrode, and the compositions of the electrolyte in terms of salt use and in terms of organic solvent, no protic solvent. So this is a classical example of a galvanic chain concerning a lithium-ion battery. So we have the two currents collector, the negative and the positive in chopper. We have actually the negative electrode composed in graphite or carbon matter. So we have a generic number of X lithium atom for a generic number of carbon atoms. Why I'm saying here with an X, a generic number? Because we have a generic number of intercalation atoms of lithium that are asking due to the working of the reaction of the battery. Because when you're closing the circuit from the very beginning situation at full load, lithium cations try to ask from this carbon layer and they are decreasing their quantity. So it's important to say that when we are at full load, so when the battery is completely charged, if we are imagining to use graphite as carbon support in which lithium is intercalated inside, it's important to say that the maximum amount of lithium that could be present is 1 atom of lithium for 6 atoms of carbon. So 1 atom of lithium for single rings in graphite, remembering the hexagonal structures of the graphite. And obviously when we are proceeding the reaction, the currents start to flow. The currents start to flow because lithium is asking as lithium plus in a certain number. Obviously this X, it will decrease because we are decreasing the amount of lithium with respect to the amount of carbon atoms when the reaction is proceeding. Then we have our generic lithium salt, in this case is lithium isofluorophosphate, is the best one, but we can even have other types of lithium salt, lithium cations complex, in an organic solvent, propylene carbonate or diethyl carbonate or ethylene carbonate, for instance. No protic solvents, since we know what is the reactions between protic solvents and lithium, releasing hydrogen and cause even explosion. And we have our lithium oxide. It could be lithium cobalt oxide, lithium manganese oxide, lithium iron phosphate. Extremely interesting because it represents a situation in which lithium is more stable, and so spontaneously lithium tend to pass from this zone to this one, be intercalated inside this oxide, and this ensure the working of the battery since the reaction is spontaneous. And in this case we have 1 minus X, because at the very beginning the amount of lithium is reduced, is basically because at the very beginning we can say that this X is equal to 1. So at the very beginning the total amount of lithium was present inside the graphite, but when lithium, the reaction is proceeding, current is flowing, lithium is passing from this electrode to this electrode, and so the lithium content in this electrode decrease, and so this X decrease, but at the same time, since this is decreased, also this is decreased. And what does it mean? That this difference decreases and the amount of lithium is increasing. So this galvanic chain tells us that when the reaction is proceeding, the amount of lithium is decreasing inside this graphite layer, but is increasing inside the oxide. If you want to define this with a semi-reaction, for instance concerning the discharging process, we can say that on the negative pole we have the lithium in a non-stable situation. So we have lithium in graphite, for instance, or in a carbon layer. Obviously we have described how this proportion is equal to 1 at 6 when we are at full load and if the carbon layer is graphite. And so this is an oxidation in which we remain with our carbon layer that now is not filled with lithium anymore, plus X time lithium plus X electrons. And then we have the positive, so we have the emigrations of this generic number of lithium cations always higher due to the proceeding of the reactions inside the electrolyte, allow the passage due to a proton exchange membrane and entering in the lithium oxide. So the lithium oxide starts from this situation. And here we are the reduction of the cobalt, the metal, due to the intercalations of lithium. And since here we are summing X with something that is 1 minus X, the result, the final result, is lithium, cobalt, oxide. So we have increased the lithium content, and we have passed, in this case, from lithium 0 to lithium plus, so an oxidation. This is acting as an anode. And in this case, the cobalt is passing from 4 plus to 3 plus, and so it's a reduction. So we have the reductions of the metal, and we have the cobalt, and we have the oxidations of the lithium due to the passage of lithiums from these to these electrodes. So with respect to other types of batteries, what is extremely different, and particularly in lithium-ion batteries, is how the work of the batteries is due to lithium at one time inside one electrode, and then inside in the other one, and so on. So obviously the opposite reaction is associated with the intercalations of lithiums from this stable situation, lithiums in the oxide, inside the graphite. So at the very beginning, during the first recharge, we need to pass from this situation to this one. And so basically we have the flowings of the electrons in the opposite direction. So now it's interesting to think about some detail. So we have described the main aspect of these types of batteries, but it's also interesting to describe some details. For instance, the fact that often if we want some of the studies concerning the state of art of the modern research about lithium's ions batteries are involved in changes in the negative electrode and changes in the electrolyte. So changes in the negative electrode in order to increase the specific energy, so maybe to increase the amount of lithiums that can be introduced in the support with respect to the weight. And so for that reason, silicon negative electrodes are starting to be studied and investigated. And with silicon negative electrode with respect to graphite, we can increase the energetic efficiency. But we have a problem concerning the expansion and the compression due to the intercalations of lithiums and the intercalation. If we are using a silicon support with respect to graphite, during the intercalation we have a huge expansion and a huge compression during the intercalation. It's a too much elastic support. And for the reason, it cannot be used as single silicon as support. And for the reasons, some research are studying the use of mixed electrode composed in parts of graphite and one portion in silicon in order to avoid an excessive compression and expansion, at the same time increase the energetic efficiency. So other types of interesting studies are involved in, for instance, the possibility to use solid electrolyte. So maybe dissolve this lithium salt in something that it could be solid as polyethylene oxide, or maybe a gel. Often we are using a solid matrix that is simply swelled with a common organic solution in which lithium salts are dissolved. So for instance, we are using the so-known polyvinyl fluoride, so polyvinyl fluoride, having these repeating unit, that is basically a polymer that is used in order to create a matrix, and this matrix, solid matrix, is welded with the use of propylene carbonate or ethylene carbonate, the well-known organic solvent in which lithium salt is diffused, because in this way we are even improving the mechanical resistance of the electrolyte and the stability of the batteries. But it's important to say that nowadays the use of solid electrolyte is, even if it's the future, because we can fight some safety problem concerning the use of these types of non-aqueous system, we need to have to solve some problem concerning the capability to investigate better the recharging process, to ensure a good contact with the electron, and also sometimes, often, these solid electrolytes are not so conductive at room temperature. And other types of possible solid substitute, it could be, for instance, ceramic lithium oxide, because due to their intrinsic lithium nature, are able to vehiculate the passage of lithium cations inside their structure. So this is for what concerns the electrolyte, and nowadays even the use of electrode doped with some halogens are involved in order to analyze the possibility to use even an aqueous electrolyte, but this is represent the state of art of lithium-ion batteries basically. One important aspect they need to say concerning these types of devices is the fact that we have a very low self-discharge, but the self-discharge is present. And why we have this self-discharge? And this is due to the tunneling of electrons from graphite to the electrolyte. What does it mean? So we know that basically one interesting phenomenon occurs during the very first charging process. So when we are building a lithium-ion batteries, remembering that we need to build it in a controlled atmosphere in order to avoid the presence of humidity and even avoid the interactions between lithium and nitrogen. But what is important in this case is that at the very start charging process, when we are building our battery with the lithium completely present in the oxide and not present in the graphite. So when we are building our batteries, we are building it with the lithium in the very beginning completely present inside the oxide. And we need to provide a first recharge with an electrolyzer. So we are providing a first recharge in order to make the lithium batteries useful for another application, and we are promoting the intercalations of lithium from the metal to the graphite in a non-stable way. This is why we need an electrolyzer. But what is happening is that when electrons arrive here in the graphite, they arrive in order to compensate and balance the positive charge due to the lithium cation. But what is interesting is the fact that these electrons can maybe react with the molecules present inside the electrolyte, the solvent molecules for instance, and cause the degradations of the electrolyte. So the electrolyte can take these electrons with respect to lithium plus and lead to the degradations of these. And what is important is that at the very beginning, during the first charging process, a particular type of layer is created here. Is created a layer due to the reaction between lithium cations, electrons, and solvent molecules. Because when lithium is being intercalated inside the graphite, it is surrounded with a shell of solvent, the same solvent that describes the electrolyte. And when these lithium cations surrounded with solvent is moving in this direction, electrons are taken here, and we can have a formation of a layer that is known as solid electrolyte interface. So we are creating this solid electrolyte interface that is a sort of magic phenomenon, a sort of magic barrier that is a blessing. Why? Because it's able to avoid further degradations of the electrolyte. At the very beginning, during the first charge, this SEI layer, solid electrolyte interface, is created between the electrolyte and the graphite, and it protects the graphite from the passage of electrons, and so it protects the graphite from the battery from the degradations of the electrolyte, the self-discharge, allowing, from the other hand, the passage of lithium plus. So this SEI, it represents one extremely interesting phenomenon that should be optimized in terms of thickness and in terms of compositions due to the first charging process, in order to create a barrier that can protect the batteries. So it's important to say that even if the SEA is extremely important in order to protect the lithium, the electrolyte from the degradation, lithium-ion batteries can follow a self-discharge process. So if we are not using a lithium-ion batteries for a lot, we can appreciate that these batteries can die. Why? Because even if we are protecting the electrolyte from the passage of electrons, and so we are protecting the electrolyte from degradations, times over times, we can have the tunneling of this electrode from this graphite to the electrolyte. And so even if a layer is present, we can have the tunneling. And what does it mean? That we can proceed with the degradations of the electrolyte. And so the SEI layer increase due to the degradations of the electrolyte, due to the tunneling of electrons. And time after time, this layer tries to increase more and more and more until the electrolyte is completely consumed and the battery will die. And if we are not using these batteries, these types of process is quite limited. But when we are recharging it and using it and recharging it again and discharging it and recharging it, so we are actually using a lot our batteries in each single charging or recharging cycle, we can have the expansion of this layer in a fast way with respect to tunneling. And so basically what's happening is that every time we are using a lithium-ion batteries, we are increasing the thickness of this SEI. And the generation of a too much thick SEI is the reasons for which the battery simply died when we are used it for a lot of times. So basically the reasons for which we have the self-discharge is due to the tunnelings of electrons over these types of protection layer, but basically that cause an expansion in the thickness of this layer itself. And when we are using it, we are promoting the speed in which the expansion of this solid electrolyte interface occurs, and so the battery will die in a smaller time if we are using it a lot. So basically we have defined more or less all the main important concepts concerning the lithium-ion batteries. Obviously, remember I missed to say that we have a decrease in the electrode profile. We have a decrease in the electrode profile when the batteries is working. For instance, an increase, when we are discharging the batteries. At the very beginning, when the battery is completely charged, the DDP is equal to 4, and when we are approaching the discharge, is passing from 4 to 3 volts. And this is due to the fact that here we are decreasing the amount of lithium, and so the electrode potential is starting to increase, whereas in this case, the electrode potential, since we are filling it with lithium, it starts to decrease. And so since this increase and this is decreased, we are filling the gap and the total DDP is decreased. If we want to describe, for instance, the profile of potential on this electrode, so the potential associated with lithium plus redox couple, with respect to the level of lithium in the carbon layer, we can say that when the level is maximum, the electrode potential is minimum, and so we have the maximum difference and we have quite a huge DDP. But when we are decreasing the amount of lithium, we can have a step profile. So basically we have difference plateau, and every time we are passing from different steps, each steps with each plateau is associated with a different degree of intercalation. What is happening is that we are increasing more and more the electrode potential, trying to minimize the gap between this electrode potential and this one, and so what is actually doing is that we are decreasing the final DDP. So this is extremely important, because each of these single stage 1, stage 2, stage 3 are associated with different level of lithium intercalated. Maybe in the stage 1 we have the complete intercalations of lithium, this is completely filled, but maybe here we have a little smaller types of lithium, and here we have even a smaller lithium again, and so on. So we are decreasing the number of empty layer of graphite between filled layer of graphite with lithiums by promoting the dischargings, and every time we are decreasing the amount of filled layer within increasing the amount of empty layer, we have a changing in the potentials profile following this plateau trend and increasing the total electrode potential, decreasing the final DDP. And this is what is important to say about lithium-ion batteries.